him, everybody is using his inventions. This is something that I often say, that it is amazing to think that Chenming, who invented the FinFET, every time we are turning on our smartphones or or turning on our computers, everything that we are doing in terms of computing is actually using his invention. So that is a very humbling feeling to have. There is not too much to say about the recognitions that he has gotten. He has gotten the U.S. National Medal of Technology from President Obama, and basically every award that you can think of in the field of electronics. So let me just say that Professor Hu has been a tremendous mentor for me personally. So I wanted to take this opportunity to thank him for that. And also the fact that he has been a tremendous role model for all of us, not only at Berkeley, but all over the world. So we are all looking forward to what he has to say about the news and future of semiconductors. So let's welcome Professor Hu. Thank you.
Thank you, Saif, for that introduction. I probably should stop here where I'm still ahead. I want to say that I think Saif is doing and has been doing fantastic work. I'm so proud to have Saif as a colleague. I think he is going to make a greater contribution than certainly I have done. And the FinFET work he talked about, of course, was not just my own work. I have wonderful collaborators in Professor Sujay Kim, Professor Jeff Bolker, Professor Subramanian was a postdoc on the project, and more than a dozen graduate students. Not only for the 4 years of the project period, but in fact in the decades leading to that, because all these kind of works has a long history behind that. Today, I am very happy to have the opportunity to share with you some ideas, thoughts on the news and about semiconductor, and what to make of this news, and what's the future that I think holds, what the future holds for semiconductor, in my opinion. First, a quick look at the semiconductor in the news. This is in a chronological order. So Moore's law is ending. This is no longer news, has been going on and has been acknowledged for a while. Even the public press is well aware of that. The rest are all rather fresh news within the last year. Pandemic hastens global digitization, highlighting the importance of semiconductors. U.S. Congress authorized the CHIPS Act that approves billions of U.S. dollars for R&D and chip fabrication. This is the first time in decades that I can remember. Now we have this kind of money. Hopefully, this some of that will come to Berkeley, and because of leadership of Saif, this is going to be so important. TSMC will build a 5-nanometer fab in Arizona, and just yesterday or a few days ago, it's a rumor that Samsung will build a $10 billion 3-nanometer fab in Texas, because that's the way to get close to the customers in the U.S. Next bullet is chip shortage shuts auto factories in Europe, U.S., as well as Asia. And finally, again, this is very recent, just a week or so. EU is going to use 100 billion euros for a 2-nanometer semiconductor industry, to try to start a 2-nanometer semiconductor industry. So how should we think about this? 2-nanometer indeed is very small. If you are laying atoms end by end, you probably can only fit a few 5 atoms in 2 nanometer. Of course, things cannot get smaller much longer, so Moore's law truly is ending. But why are people putting in hundreds of $billions to still invest in this industry or technology that's ending? And or is this a a dying technology that's seeing a bright tunnel, welcoming it into death? I don't think so. I think we are actually continuing on the road of rather steady progress. It's not easy road. It's a bumpy and needs a lot of work. But we are not seeing anything particularly spectacularly different that we haven't seen before. So I hope to share that thought with you. First, let's talk about this 2 nanometer or 3 nanometer. How should we think about that? First of all, what do these 7 nanometer, 5, 3, 2 nanometer mean? 2 nanometers really in the news, I believe, is this EU announcement. Well, technology node used to mean half of the line pitch. Now it only means a major new node, a major new technology. That's all. So don't read the numeral literally. So the bottom is a comparison. I think I took this table from an article that was really trying to illustrate that Intel's process technology, even for the same node, the notation is more advanced than TSMC. Now that is a fact. But let's look at the numbers here. Just look at the Intel 14 nanometer. Nothing here is pitch is 14 nanometer. You notice that? And 10 nanometer, nothing is larger than 10 nanometer. TSMC 7 nanometer, nothing is close to 7 nanometer. So when we look at the 3 nanometer, 2 nanometer, don't think we're that close to the end. Now, I'm not saying we are not approaching an end for the reduction in line width, but it's not just as bad as it looks. How do we make these lines? EUV is here at 5 nanometer. I say is here because I was just chatting with Professor Andy Neurather. And in the late 80s, he actually coined this name, extreme UV. It's because 10 years before that, throughout the 80s, people have spent lots of money developing the technology, but at the time was called soft X-ray, and so people are getting tired of it. And Andy says, "Oh, let's call this EUV." I think it's a brilliant move, and the investment continued. It takes this long for us to push the technology forward. And this is echoes what I said earlier. Even FinFET actually is a result of decades of looking at the problems. Because of that, 5 nanometer TSMC technology, they call it M5. They don't call it 5 nanometer. I think that's better than 5 nanometer. So M5 is uses a fewer number of masks than N7. So clearly EUV reduces the overall cost and increase the yield. Otherwise, industry would not adopt it. Nonetheless, making these very small geometries is expensive. We cannot, we don't dismiss that at all. And that's a fact, and it's a problem. It's a difficulty, barrier. And it's for this reason that we're going to end somewhere, even with the EUV. Of course, there's hope that there are other ways to make the small lines, perhaps something called the self-assembly. But the interesting thing is that, the high expense, high cost doesn't necessarily, maybe counterintuitively, is not necessarily a bad thing for the industry. The reason is that these small geometries give us such high speed, high performance computing and communication capabilities, and they are worth a lot to the world. And as a result, the ASP, or the average selling price of chips, can now, for these advanced chips, can be many hundreds of dollars a piece, can even go into $1,000. And so you could argue that our semiconductor industry has been given a wonderful technology to the world too cheap. And when that's because the very healthy competition industry. But when no one can make this cheap, and the world is going to pay for it because it is so important to the growth of the world economy and to improvement of the quality of life of the population of the world. For example, I believe I copied this web screen capture this in 2018, probably. So I was curious, how to think about the how NVIDIA think about the artificial intelligence, AI. As you know, that's probably the most exciting new technology that has come along in decades, artificial intelligence, and in this last 5 years, the biggest beneficiary company from AI is arguably NVIDIA. It now has a market cap way ahead of Intel because they made the first GPU that's good enough for practical use for AI. So that's the important thing. And so I was curious what NVIDIA says. I typed in NVIDIA AI, and Google took me to a site called the NVIDIA AI Solutions. And the first screen I see in that NVIDIA AI Solutions is this. NVIDIA says 16 nanometer FinFET for unprecedented energy efficiency, with 15 billion transistors built on bleeding-edge 16 nanometer FinFET fabrication technology. Pascal's GPU is the world's largest FinFET chip ever built. And when you have these kind of small geometry, you can have such high packing density. And the only reason you can have the high packing density is because energy efficiency. So when you can pack this circuit density in, you can do wonderful things that the world never dreamed that can be done. And of course, now NVIDIA uses 7 nanometer and it packs 54 billion transistors in it. And in fact, the packaging is also puts on hundreds of billion of transistors. I'll mention that how that's done later to also. So it's difficult journey that we are all taking, but it's worthwhile, and the world will fund it, because as long as what we are doing is useful, and clearly there's no sign that we are not doing very useful things. So, this lead me to want to share with you my thought on what makes semiconductor different from the other technologies. The world has seen technologies come and go. What's special about semiconductor technologies? Well, I think the first thing is it has very wide applications. It actually lifts all the industries and technologies. Semiconductor enables not only computing, that really revolutionized the way we study chemistry, biology. It also gives us hardwares, electron microscopes, and every instrument is so different. DNA, genome, everything relies on semiconductors. That's why we could have a few $100 whole human genome, at least theoretically. And people are actually fighting to make that cost to below $100 entire human genome for each person. And semiconductor really lifts all the technologies. If you think of metallurgy, and we're going to design DNA not for health purpose. Michael, I didn't do anything. Are you still seeing my shared screen?
No, we lost your shared screen.
I'll try again. Hopefully I can get back.
Yeah, it's back.
It's back? All right. It's
Yeah.
not back for me. Let's see how to do this. Okay, it's back now. All right. So I was saying, design genome, DNA, it's not just for going to be for health purposes or studying biology. It's going to be the new manufacturing technology. Lots of things can be manufactured through designed DNA, and I believe even a semiconductor can benefit from that. I'll get back to that with example later. Second bullet is that, semiconductor industry uses relatively small amount of material, right? If you look at silicon, it's second most abundant material on Earth, and everything uses relatively small. I'm not saying that's not a concern, manufacturing energy, but relative to other technologies, it's relatively small amount. So it doesn't put as big a footprint on the environment as many other technologies, such as auto and oil industry. They have already been here for 120 years and still going. But the even more amazing is that in this technology, smaller makes the work better. We want to make things smaller. Of course, smaller means less material use. But when we make semiconductors smaller, it actually is faster. It actually is more energy efficient in operation, not just in fabrication. Now, what else? What other technology can you say for that? Can you make the plane smaller and carry more people? There's nothing else you can say about this. And the next bullet is that theoretically, and Saeed knows this better than I do because he just found ways to beat this. There's still more than 1,000 times energy reduction possible theoretically. Now, I'm not saying that we will get all there, but we'll get 10, 100 times improvement. I'm sure of it. And when we do that, we probably will find ways to squeeze some more out. So the point is that we still have time to get 100 times more ability to solve problems. That's what it is. Well, that's what a semiconductor does to the world. It's give us the last bullet says it increases humans' ability to solve problems. And in the future, there will be much bigger problems. You can imagine bigger problems that semiconductor has helped to solve in the last 50 years. 50 years ago, every country is pushing birth control because there's no way to feed the people. Now every country is wanting to have more larger birth rate, and no concern about food supply now, no concern about the problems, and I'm sure global warming is going to rely on technology to deal with. So back to the smallness of the line, and this is most of you, I think, know ITRS, and it's a second reincarnation. IDRS is a industry group committee that meet several times a year and that makes certain projections. So according to this group, if you just look at this as a node, supposed to be 5 nanometer, EUV can bring us to 3, to 2, and to 1. And with that, the half pitch can continue to reduce and even give us some timeline. But after that, it says it believes that it's going to be not economically attractive to further reduce the line width. Instead, we're going to start to piling things up, multi-layer. This is not just by packaging, but monolithically on the silicon wafer. You're going to grow more than one layer of circuit. And you're probably going to have 2 layers first, and 4 layers, and then could be 6 layers, 7 layers. It's not unthinkable. After all, NAND today already have 126 layers on it. So this is the way that this group thinks. And I think this trend definitely is right. Now, whether this timing and whether the end point is right, this group does not have a very good track record, I have to say. And this gives me a segue to say something about the how the FinFET came about. 1999, and this is the this group's prediction. It's a roadmap, just pretty much the same as the previous slide. They publish a new roadmap every year. So 1999, this is what the this group says. Says that at that time, 100 nanometer is, I believe, in production. It's always a year or so late, and 100 nanometer is being developed. It's so the group called this being pursued, and the second row says it's gate oxide thickness. I highlight this because the group also highlight this item as the one that you cannot be scaled much further. So 1 nanometer is being pursued. 790 nanometer is going to need oxide thickness about 1 nanometer, and 50 nanometer technology in less than 1 nanometer. 35 needs to be about half a nanometer of oxide thickness in order to control the leakage current for the offstate current, turn off the short channel transistor. And after that, it doesn't think it can be done. There's no solution. That's the end of the roadmap. That's what the committee says. This second row actually was not incorrect. We cannot make the gate oxide infinitely thin. And in fact, if you look at the electrical oxide thickness, EOT, even today, we are not getting this thing. 0.7 nanometer is what we're using, EOT, including the high K. So that part is not wrong. But what's wrong is that it says cannot turn off the transistor if we don't scale the oxide thickness. And this is because textbook has long taught all of us, and I have used the same textbook to teach my students, that if you want to reduce the channel lengths, you also have to reduce vertical dimensions, mainly the gate oxide, in order to turn off the transistor when the gate length is very short. But turns out that that's wrong. And but anyway, companies, this happened to be, unfortunately, my friend Paul Peckin, Intel, wrote a widely discussed the science article with Intel's name on it in same 1999, pointing out that yes, gate oxide just cannot be scaled, and then junction depths cannot be reduced, and random dopant fluctuations fundamental. And so this is why we're coming to the Moore's law is going to end. But in the same year, 1999, and this is what Saeed mentioned, the Berkeley device group published this IEDM paper showing that already we can make 45 nanometer with better subthreshold swing, much better leakage current than the production 130 nanometer transistor. And we didn't use half a nanometer of oxide, we just used 2.7 nanometer oxynitride. And We don't even need heavy doping to stop the leakage current or punch through or ultra shallow retrograde doping. We don't need any doping to control the leakage, and that's that. And that's the what FinFET can do. So I will not go into the physics of that. I think most of you already know why FinFET can overcome all that. But the important thing is that FinFET showed a new direction. The old rule was that LG scaling scales with TOX, body doping concentration, junction depth. The new rule says that LG scales with the body thickness. In other words, what really is important is to think FinFET as a thin body device. You know, this is the body, yellow is the body. You just have to make body very thin. If you can make the body thin, you can continue to reduce the gate length, and you don't have to really reduce the oxide thickness. But of course, oxide thickness is still beneficial. That's why we are using 0.7 nanometer EOT now. And in fact, we also even point out quantitative correlation. That is, you know, if you can make a certain thin thickness, then the gate lengths can be as small as twice of thin thickness. You know, this number 2, of course, you can argue whether it be 3 or what. It depends on your spec for leakage current. But basically, if you can scale the thin thickness, then you can reduce the gate channel length. So this is one example: extreme thin and thin. So this thing are etched. And this idea of thin body being the future for scaling is also demonstrated in 2001 by even shorter even shorter channel lengths by the same FinFET group. We call it UTB, and today the common name is FDSOI, very thin oxide, SOI film. So we use the 3 nanometer SOI because that's thinner than what we can etch the thing, and so we could make it as small as the E-beam allow us to make as a transistor gate. And in 2006, Samsung demonstrated another way to make a thin body. In this case, it uses epitaxial thin film. So they use a clever idea of epitaxially grow a few nanometer of silicon, then some sacrificial epitaxial silicon germanium, then a very thin silicon channel. And after that, you know, they will etch away the sacrificial silicon germanium and use this too thin silicon film as the thin body to make the transistor. So they call that the multi-bridge FET. And today, the industry called the gate-all-around or GAA. I'll say more about that because that's an important near-term new technology. So those are the other options of making thin body transistor option to the thin. And so this slide says the FinFET is also a 3D FET. One is that it's a thin body FET to allow the gate scaling. It's also a 3D FET. This is very important. In fact, this is the reason that you know, we prefer the FinFET over the FDSOI, although FDSOI is easier to make. Because tall fin means very large W and a small area. It's like building tall buildings in a crowded city. You know, you don't want to build single-story buildings anymore. You have to build up. So it started this 3D direction, and that I think is going to really be the future of increasing density when line width scaling is going to end. So it's 3D going up. So as a result, the thing has been made thinner and taller every node. Now this again is collection of Intel's FinFET, the first generation 22 nanometer, and look at the 14 nanometer thinner and taller. 10 nanometer, it's a 7 nanometer thin, and 55 nanometer tall. So when this thing cannot be made thinner and taller, then people will go to the GAA, turn it around. So right now, Samsung says they plans to make the 3 nanometer GAA in 2022, and there may be delay because of pandemic. TSMC says it's going to use 3 nanometer for FinFET in 2022 and 2 nanometer GAA in 2023. Now clearly, Intel is feeling the heat of Samsung's GAA, so it's a very impressive schedule there. Of course, I'm sure TSMC has been developing a GAA for many, many years already. So, So in other words, all right, just look at this. So this is IBM's way of thinking about GAA. So it says, you turn the FinFET to nanosheet. Oh, by the way, another name for the GAA is nanosheet. And IBM like to use that, but the industry have more or less converged on GAA. So it says, think of the nanosheet this way. You have a FinFET with 3 things, right? Because often we use 3 things to make transistor in order to get enough W. Instead of using 3 things, how about you turn the 3 things 90 degrees and stack them one on another? So that's the way to think about the nanosheet, and that's the way I think about nanosheet as well. So you do that, then you can continue to make, you can make this body thinner, then you can etch. It's just a technology having to do with etching, with the cleaning, and I guess etching is more important rather than cleaning, because this needs cleaning too between very thin sheet. But certainly everyone expect epitaxy has more ways to go in terms of making the body thinner. For the designers, this is also a more flexible transistor structure because IC design can specify the nanosheet width. As a result, you can get continuous transistor W, especially with the EUV. With the optical lithography, often we limit the line width people can do. Perhaps we will do that soon as well. So as a result, this design is going to be more flexible than the FinFET design, because FinFET you can only specify 1, 2, 3, 4 discrete number of things. So the W is not continuously adjustable, but nanosheet will allow that. And by the way, this is a SEM picture, TEM picture of how the 3 nanosheet are stacked together. It's expected that the first generation nanosheet will be 3 nanosheet stacked. If it's less than 3, just not worth the trouble to go that direction. FinFET will be still more economical. Now, how do we make this nanosheet structure? Very briefly, it really has to do with growing the red sacrificial silicon germanium epi on silicon, and then grow the silicon channel, and you repeat it several times. Another red silicon germanium, another gray silicon. After you do that, then you etch away the red and leave the silicon. And this is shown here. The silicon film is hanging. The red has been etched away. It's held up by the source drain, not shown here. And now you put the dielectric around this nanosheet, and you put the metal gate. And here is another way of showing you, if you do 3 of those, then this is what happens. And of course, at this time, the ends are being held by the sorting drain. You cannot see. So here's a demonstration that, hey, we could actually make more than 3 if necessary. This is now 6, and people have even made more than that. Now, you don't have to use them all for N-channel. You could possibly consider making them N and P, and that's another way to do that. So this then leads to this idea of going to the multi-layers. And even more interesting way to make multi-layer is that we're going to use 2-dimensional semiconductors. They are very thin because they are the ultimate thin body. You can make them only 0.6 nanometer thin. So you can make the gate lengths as small as we can imagine. We're truly counting atoms there. And Professor Ali Javi has done a lot of work on this. And you can grow a single crystalline film of this on silicon substrate, 12-inch, and then transfer it onto silicon dioxide. And you can do this transfer many layers. Here it shows 2 of these layers, but you could have 4. And this then how you make the monolithic 3D ICs. So material layer quality is still to be improved. And perhaps because of that, the carrier mobility hasn't yet met the theoretical promise of being 5-10 times better than silicon at such thickness. And if we can have that kind of high mobility, we don't need multi nanosheet GAA. Just 1 sheet is enough for a transistor. So that could even make the fabrication cheaper. And the circuit and process architecture still has to be worked out. It's a lot of work that can be done. Another exciting thing is that 3D packaging. And you may hear other words like CoWoS. Now that's TSMC's trademarked chip on wafer on substrate. Another word I really want to introduce to you is people call this chiplets. So this is the idea that you can use package to put lots of memory dies and GPU, CPU, ASIC chips all together very closely. Essentially, you can think of this being possible by a new kind of circuit board, if you will. The circuit board is actually 12-inch silicon wafer. And using the back-end process, it make very complex and very high-density interconnection to connect these chips. And not only that, there's something called through silicon via. Then the silicon 12-inch wafer can have holes and actually through the thickness of the wafer, and the holes are filled with copper that allows this chips, this package to be further connected with other such packages if necessary. So this is, the package is also going 3-dimensional. And by doing that, we could even consider these wafers, processors could be stacked together. And not to mention, last slide, I said each of this processor can have 2 layers of circuits or even 5-6 layer of circuits. So that's the direction. So GPU, CPU, heterogeneous integration of 3-5 lasers, silicon photonics, they are all happening. Maybe they are not on the market yet, but they soon will be. And they are all being done today. It's just a matter of years, if not months. But I want to emphasize that low power actually makes high IC density possible. You know, how can you stack all these chips? Each already has 50 billion transistors. How can you put 20 of them on a small waveform? The only reason is that we expect the transistors and circuits to use 10 times, 100 times less energy and per function, and this must be the goal, and the industry wants that. I say industry wants that, so here I want to show you a slide that Intel's senior fellow and director of, I think, forgot the director of some technology, exploratory technology, Robert Chow, gave this talk just last week at NSF workshop on future of semiconductor and beyond device and technologies. So I attended this workshop as well online. And here's one slide from that. He said, solution is lower voltages drive higher energy efficiency. We just have to make transistors operate at lower voltages. And he says Cmos 0.8 volt, people are using 0.7 volt, and now tunnel FET can go to 0.4 volt, ferroelectric FET can go to 0.2 volt, and this is the one I'm going to show you another slide later. Spintronics can get to 0.1 volt, although the speed is not as good as these as the ferroelectric FET and the Cmos. And here the last line I want to read with you. Provides device level energy improvement of 10 to 100 times. And this is what industry wants. They want it today. And I think they are not quite there yet, but they think they can do this from two times, then to 5 times, then to 10 times. And the ferroelectric is the one I want to say more. And this is really an invention of Professor Salahuddin. I think this is going to be a game changer. I think, I have to believe that industries are all, companies are all working hard on this. Perhaps because they are working so hard, they are keeping quiet about it. It's my personal guess. And so Professor Salahuddin called this a negative capacitance transistor. It's fascinating. Unfortunately, I don't have time to share more with you, but it does introduce ferroelectric. And as fate would have it, very luckily, our very familiar material, zirconium oxide, hafnium oxide specifically, actually can be made ferroelectric. And so this has generated a lot of excitement. And 2020, he and co-workers had a paper in the EDL. It's a cover story. And, if theoretically we could get the same performance, same ion-off with only 0.27 volt of a power supply, and this is just exactly what Robert Chow wanted. And I believe there is even ways to further reduce this once we get on the learning curve. So this is really the most exciting thing I'm really rooting for, and I think it's going to bring a lot of honor to this department. I will not say well, I will say this blue point again. Robert Chow went on to say, needs for fundamental research, workforce education to solve the challenge. So this is really for us to do here. Every students, postdocs, professors, devices this interconnect based on atomic scale materials and their interfaces. Manufacturing tools for new materials and interfaces, chemistry for atomic self-assembly. I would add even biological self-assembly, I think is going to be needed. Modeling of new materials and processes, solving industry's fundamental materials challenges, and what novel interfaces are required, and focus academia partner on these challenges. So I'm doing a time check. So it's probably good for me just to show you 2 examples of our own professor's work. This is Professor Subramanian, 2012. I did not look for the publication citation, sorry for that. He showed that through organic chemistry chemistry synthesis. He could make a molecule itself contain semiconducting part, insulating part, so that he could make a transistor just like that. So one molecule could be a transistor, and it can be stacked this way. And Professor Jeff Boker gave me this 2006. It uses making markers using lithography, and then add materials, use DNA or other large molecule to put new materials at specified locations and directions from the marker. And that's the way for the self-assembly to go, or directed self-assembly. So we're not going to entirely go away from lithography, but we can greatly reduce the number of lithography steps, and that's the way to keep the cost from blowing up. And I will just say that semiconductor, and really it's a microfabrication technology, is an irreplaceable infrastructure. It's not just for CMOS, but also for, and itself will benefit from photonics, spintronics, biointerface, neuromorphic computing, quantum computing. So that with this infrastructure. And I hope our department will continue to invest in this direction. It's expensive to get the fab continue to refresh, but I think we all have found that the fab, nano fab at Berkeley, not only benefited so-called semiconductor or CMOS, it actually benefited just about anything, everything we do here. And this example, the graphic example I put here is the qubit, that is the most promising qubit. And, I'll just read that. Two quantum wells are formed in the top corner of the nanowire. Just think of this as the two top corner of a FinFET, if you will. So we can design this so that there are two quantum wells, and in that quantum well there is the phosphorus. And by the way, the silicon is perfect because we can have isotope-free silicon because of the material technology, so that there's no spin noise. And the electron spin of the phosphorus atom in this quantum well forms the qubit. And qubit control is achieved via spin, electron spin resonance techniques with microwave pulsing. So I will stop basically here, maybe with one summary. I'll stop here. So better electronics helps ensure peaceful global growth. I think we all want that, peaceful global growth. We need to explore chemistry, physics, biology for future electronics. And there's no better place to do it than in the university. And it's going to be hard, but we must keep climbing this hill till we see new vista beyond the ridge. Semiconductor road has always been like this. FinFET came up just as people thought there was no road ahead. And now people think there's no road ahead, but there will be new road ahead, starting with the NCFET. And each of these breakthroughs will buy us 20 years to find the next breakthrough. And this will bring us to the end of the century. I'm convinced of it. All right, I will stop here. Thank you very much. And I apologize not leaving in as much time as I would like for the questions, but I can stay longer. Most of you need to leave. Please feel free to leave. Michael, back to you, or Saif.
Thank you very much. Saif, do you want to do the question session, or?
Michael, maybe you control it because you are the host.
Okay, yeah, very good. So we have a lot of applause on the side, virtual applause.
Thank you.
But I'll open it up for questions, and we still have more than 160 people on the call. But maybe let's just try it. If you have a question, please unmute yourself, and we'll see if this works in this way.
I have a question.
Yeah, please.
Hi.
It's Eli here. You mentioned at the beginning that there's a shortage of semiconductors for the automobile industry, but the automobile industry, to the best of my understanding, doesn't always use the leading edge semiconductors. So is it a shortage in the leading edge, or is it in the older foundries?
Indeed, not all the applications will need leading edge technology, so it's not. But the fact is that there are many other electronics applications that also don't need leading edge technologies. So in the early months of the pandemic, auto industry thought that they're going to, see a slump in the sales this year, so they reduced order or canceled orders. Of course, the capacity was picked up by the laptop and all the other applications. So when the auto industry found out the demand is much stronger than they thought at the end of the year, they couldn't get their orders placed anymore. So that's what it is. In terms of what the future is like, there will continue to be a lot of these, as you say, non-needing technologies, because they are important. They will also going to continue to grow. But TSMC's business, for example, 60% are in the cell phone and the computing. They require the leading edge technology. So that's why a lot of emphasis is about leading edge technology.
Thank you.
Are there any additional questions? Please don't forget to unmute if you have a question.
Can I ask another question since nobody's speaking up?
Go ahead, please, Eli.
I'm very curious about the concentration of germanium for the selective etching of the thin layer transistors, the multi-layer transistors. What percentage of germanium allows the selective etching?
Well, I don't know that. Professor Sujie King Liu would be the expert on that. But my understanding is that it does not take that much to create significant etching rate difference. So much so that people think they could even, etch away the sacrificial silicon germanium and still leaving active silicon germanium, not just pure silicon, as the active channel. So it's that's the wonderful thing about this, what I call this a semiconductor infrastructure. It's just so valuable. Not only we can do these things at a very small scale, with great finesse, we can do this with such a low defect density and wonderful uniformity. And these are the things that quantum computing will have to have, for example. So yeah, I don't have the answer for you, but I think it is quite flexible, the way it's the new technology and the tools, of course. Now etching can be done called atomic layer etching, as you well know.
Thank you very much.
I have a question. Thanks so much for the beautiful talk. What do you think is going to be the most feasible way for 3D integration? Is it going to be monolithic 3D, or is it going to be some kind of stacking like you showed through vias?
I think that question is answers already there. That is the through the package, through Silicon Via, and by the way, there are a lot of innovations there. It's already happening. That is in fact, how the most advanced chips are used. They are all put on this chipset close to stacked memories, and so there's no question that's going to continue. The monolithic is still, at this point, is still a work in progress. But as you can see from the ITRS roadmap, the industry group expect this to happen. It put this at 2030 about. So we still have, close to 10 years to really work out all the kinks in that. And once it starts, the start is always the hardest. And then, we might see many layers as time goes on, monolithic.
Thank you.
I have a question. I'm wondering, do you see ferroelectric FETs replacing Cmos in the future, or how do you see that? Thank you.
That's a really wonderful question. And this is the beauty of the ferroelectric FETs or NC FETs. It doesn't replace CMOS. It is CMOS. Just like quantum computer will be built into in a MOSFET, in a CMOS. That's the beauty of it. I said in one of the last slides, bet with semiconductor. If I said bet with CMOS or bet with incremental improvement, that's probably what I really meant to say. This industry really favors incremental improvement. It just cannot handle whole-scale scrap down and build up again. Just not possible. The job is economically not feasible. So it's always a small step at a time. And this ferroelectric FET or FinFET really have that feature. You won't even know the difference. When it introduced, if the company choose not to tell you, you probably don't even know it's using it, just a little bit. And not to mention, because your ferroelectric in the gate, certainly very attractive to see how memory and computing could be done really in close. So it's not replacing CMOS. I think it's just going to enhance CMOS. It's a natural growth of the CMOS. And this is a part of what said earlier about semiconductor always being a steady, although bumpy progress. But it's a steady, it's really no large interruptions.
Thank you.
Professor Hu, this is Ranzi Chen. Yeah, thanks for the nice talk. I have a question regarding a statement of Moore's law is ending. So yeah, it's what we see. The voltage scaling is very much slowing down, and the gate oxide, as you mentioned, EOT is not much scaling. So from your view, the question is, do you see more nodes coming out in the coming years? And also, if we don't call them Moore's law nodes, how should we call them?
All right, Renchi, thanks for that question. Yes, I do see nodes coming out. In fact, even this ITRS industry group predicted that when the line width stops, and so when I say Moore's law is ending, I really meant it in a narrow sense, that is line width scaling is ending. I actually do believe, emphasize that 3D stacking, both packaging as well as monolithic, is in the future. and this ITRS group actually says it's coming in 2030. So we can see that there will be many nodes coming up.
Thank you.
And in that sense, one can argue, and I believe Intel will argue, that Moore is not ending. And I will not say they are wrong, because if you interpret Moore's law as the density, it actually will continue to increase.
Thanks.
This is Andy Newrider. Can you hear me okay? I just
Okay, I think with this, we probably should stop here, and really want to thank Professor Hu.
Mike, Andy was asking a question.
Oh, sorry, I did not hear it.
Let him, yeah.
It might be a good note to end on. In the 70s, silicon was called the new steel because the revolution that the steel caused would be duplicated by silicon. But today, it's more like the new sandbox for electrical and magnetic and even quantum effects. So anyway, good luck with getting people to follow that. And I think in the 90s, the National Academy of Engineering did a study of what people would raise their taxes to support. And the only thing that was qualified or was above 50% was the medical profession. But I think this is so enabling of so many fields, it might actually reach that level of public approval.
Yes, and I think this industry will help the public health as well. So, you know, so what we are talking about is really not a new material. It's a new platform. And I think this platform is unparalleled, unprecedented. And that's why, you know, I'm really gung-ho that this is going to be so important for the world, for every nations, and for our department. We have to have faith in that. And, you know, this department have had faith in this. When all the universities moved to 3.5, we stayed in the silicon. We believe it can be, can continue. And I'm not arguing for silicon today. I keep saying it's really not about the material. It's not even about semiconductor. It's a platform, and we have to continue to focus on this platform if you know, we want to continue to lead.
Thanks.
Thank you, Andy. I think that's a great ending, and I'm so glad you're here today.
Okay, thank you again. Thank you everyone for joining us, and again, thank you, Professor Hu, for this exciting presentation. We greatly appreciate it. Thanks, everyone.
Thank you very much.
Thank you.